tutorial to address a little bit about how stars form and then how long they can live on the main sequence. So fusing hydrogen into helium. Stars begin life as a cloud of gas and dust. So they're going to form out of molecular clouds. The birth of a star begins when a disturbance, such as the shock wave from a supernova, triggers the cloud of gas and dust to collapse inward. So it might be compression from a supernova. It could be that molecular cloud is going to orbit through a spiral arm in a galaxy like the Milky Way galaxy. We often find star formation associated with the spiral arms. But there is something that initiates the gravitational collapse. So imagine that you're observing the region of space where a cloud of gas and dust is beginning to collapse inward to form a star. The object that initially forms in this process is called a protostar. Will the atoms in the collapsing cloud move away from one another, move closer to one another, or stay in the same locations? Well, the cloud is collapsing, so they are coming closer together. What physical interaction or force causes the atoms to behave as you described they would in question 1? It is the attractive force of gravity. Would you expect the temperature at the center of the protostar to increase or decrease with time? Explain your reasoning. Increase, because we have to conserve energy. When the cloud was spread out, lower density, it had more gravitational potential energy. Then in collapsing, that gravitational potential energy becomes kinetic energy, and then the moving parts of the cloud are going to collide with one another, converting kinetic energy into thermal energy. So the temperature will increase, and the temperature is going to be hottest where the material is orbiting fastest. We go back to Kepler's laws of planetary motion. The objects that are in closest are going to be orbiting fastest. So that's where it should be hottest. All right. This inward collapse of material causes the center of the protostar to become very hot and dense. Once the central temperature and density reach critical levels, nuclear fusion begins. During the fusion reaction, hydrogen atoms are combined together to form helium atoms. When this happens, some photons of light are emitted, so it gives off some gamma rays. Once the outward pressure created by the energy given off during nuclear fusion balances the inward gravitational collapse of material, a state of hydrostatic equilibrium is reached, and the star no longer collapses. When this happens, the protostar becomes a main sequence star. This idea of hydrostatic equilibrium is that star has reached a point where outward pressure, trying to make that protostar expand, is just balanced out by the force of gravity causing the protostar to contract, to be smaller in size. And as long as it's in that hydrostatic equilibrium, it's going to be a happy star. Once it runs out of nuclear fuel to provide the thermal pressure that opposes gravity, then the star is going to have to change. And it's got some rough days ahead of it. All right, if we look at this table from stellar evolution calculations, we have masses of different stars: a half solar mass, 1 solar mass, 2 solar mass, 6 solar mass, and 60 solar mass, and how long they will spend on the main sequence fusing hydrogen into helium. A half solar mass star will have a main sequence lifetime of about 50 billion years. So that's even older than the universe. So every low mass star that's ever been formed is still in the main sequence at a half solar mass. The universe is not old enough for them to do anything else. At 1 solar mass, it lives on the main sequence for 10 billion years, so drop by a factor of 5. two solar masses, it's on the main sequence for 2 billion years, so dropped by a factor of 5. At 6 solar masses, so 3 times bigger in mass, we drop from 2 billion years to 110 million years, and we jump up by a factor of 10, going from 6 solar masses to 60 solar masses. The main sequence lifetime drops from 110 million years to less than 1 million years, 360,000 years. So this increased by a factor of 10, and this drops by much more than a factor of 10. All right, which live longer, high mass or low mass stars? Well, the low mass stars, by a lot. And that usually surprises people, because a high mass star has more hydrogen, has more nuclear fuel. You might intuit that it should live longer, and it's precisely the opposite, and not just by a little bit. 60 solar mass star lives in order of magnitude hundreds of thousands of years. A half solar mass star lives 50 billion years, so it's not even close. Based on your answer to question 4, do you think that the rate of nuclear fusion in a high mass star is greater than, less than, or equal to the rate of nuclear fusion in a low mass star? Well, it's got to be greater than. If the rate were equal to, then every time I jump up by an interval in mass, I would, if the rates were the same, I would have a lifetime that increased by that same amount. So going from, if the rate stayed the same, going from a half solar mass to 1 solar mass means I double the mass. I would expect to then double the lifetime if the rate stayed the same. So it would be 50 billion years for a half solar mass, 100 billion years for a 1 solar mass star. And in fact, the lifetime is actually shorter. It goes from 50 billion years to 10 billion years. So higher mass stars have to use up their fuel at a faster rate. So even though they have more nuclear fuel, they have a shorter lifespan on the main sequence. All right, which of the following statements best describes how the lifetime compare between star A, a star with a mass equal to the sun, and star B, a star with 6 times the mass of the sun? Circle the best possible response given below. Note, it may be helpful to examine the information given in the table on the previous page. All right, star A will live less than 1/6 as long as star B. So we compare a 1 solar mass star and a 6 solar mass star. No, so that's even in the wrong direction, right? The 1 solar mass star will live less than a 6 as long as the 6 solar mass star. So it can't be that. Star A will live a 6 as long as star B? No. Star A will have the same lifetime as star B. 10 billion years to 110 million years? No. This 1 solar mass star will live 6 times longer than the 6 solar mass star. So 6 times 110 million gets me to 660 million, which is way less than 10 billion. So that's not right. Star A will live more than 6 times longer than star B. The 1 solar mass star will live more than 6 times longer than the 6 solar mass star. That is correct. All right. The sun has a lifetime of approximately 10 billion years. If you could determine the rate of nuclear fusion for a star with twice the mass of the sun, which of the following would best describe how its fusion rate will compare to the sun? Circle the best possible response to complete the sentence given below. It may be helpful to examine the information given in the table on the previous page. A star with twice the mass of the sun would have a rate of fusion that is blank the rate of fusion in the sun. All right, so we're just comparing a 1 solar mass star to a 2 solar mass star. Okay. If the rate were the same in the two, then 1 solar mass star would live for 10 billion years, the 2 solar mass star would live for 20 billion years. Okay. If the rate doubled, then the 2 solar mass star would live for 5 billion years, and instead it lives for 2 billion years. So it must be the case that a star with twice the mass of the sun would have a rate of nuclear fusion that is more than twice the rate of fusion in the sun.